Okay, so final stretch. I know that all ended up being very long, and it was even longer on the videoing end because I have to keep running. Anyways, like you need to know that. So we have something that Hewitt calls force in motion, which is a way of thinking about our real world experience that an object that has mass, which, well, there aren't too many objects that don't, and has a velocity, hits you hard, potentially. It appears, it acts as if it, during a collision with you, provides a force on you. As a result, Hewitt calls momentum a force in motion. But momentum is not a force. It feels like a force when an object that has momentum hits you. It gives the effect of a force on you. We, more strictly speaking, say that you've transferred, or the object has transferred its momentum to you. Momentum, symbol P, combines the idea of mass and velocity because something hitting you, how hard it hits you, and how you end up responding to that depends on both. Because velocity is a vector, momentum is also a vector, and as we saw when we talked about the gun and its recoil, the momentum of a system that has no net force acting on it has to remain zero, or rather, it has to remain constant. The change in momentum of a system with no net force acting on it has to be zero. Its momentum itself has to remain constant. That's effectively saying that the velocity has to remain constant. There is no acceleration. But individual components of that system can have their individual momenta, their individual masses and velocities, do whatever the heck they want, as long as the vector sum for that system remains constant if there is no net force on that system. The fact that the idea of net force is getting tied into change in momentum should not cause you to not be surprised by this next slide. We have a quantity that summarizes change in momentum. We call that quantity impulse, symbol J. The idea is that in real life, we know that the effect of a force depends not only on how big the force is, but how long it's acting on you. If I hit you hard, but only for a microsecond that I'm in contact with you before you, I guess, fly backwards, then that is going to have less of an effect on you than if I hit you hard and I remain, my hand or whatever I've hit you with, remains in contact with you for a long period of time. So impulse is equal to the force times the time that the force acts through. And this is one of these other things that physicists often do, which is to say, you know, we have some concepts that we feel kind of might be related, so let's take their equations and scooch them around a bit with algebra and see what happens. That could be fun. Usually best done along with a drinking game. So, but let's go forward with this. We have the idea that force equals mass times acceleration. This is the definition of acceleration, a change in velocity over time. So we can say that force is mass times the change in velocity divided by the change in the time. Multiply both sides by delta t. That gives us force times the change in time is equal to mass times the change in velocity. Well, mass times the change in time, force times the change in time, force acting over time is impulse. Mass times the change in velocity is equal to the change in momentum. And we find that impulse is the change in momentum is force acting over time is mass times the change in velocity. A force acting through time produces a change in momentum. When I hit a baseball, I'm told not to just swing the bat and stop as soon as it comes in contact with the ball, but in fact to follow through with my swing. Same thing in golf. The idea here is that ensures that the ball remains in contact with the bat for a fraction of a second more. That fraction of a second more, while my force may not have changed, it increases the impulse, which increases the change in momentum that the ball will undergo, which, since it's not going to change the mass of the ball, one hopes, will increase the change in velocity that the ball will undergo. So the ball will shoot away from me ultimately faster, with a faster initial velocity where I'm setting initial as the time at which it comes out of contact with the bat. It will have a faster initial velocity if I've kept the bat, providing the force, in contact with the ball for a longer period of time. Impulse transfers momentum in a collision, and we will look at collisions and conservation of momentum problems in person a little bit more on Thursday.